So, all right. Okay, good morning. So, we will start with chapter 6 on fluid statics. So, we are entering into uh, fluid. So, we already studied on introduction to fluid on last week. So, this week we will continue with static fluid. So, which means the fluid at rest. So, the non-moving fluid. Okay, so the chapter will cover the introduction. So then we will study about hydrostatic forces, the forces acting under the water, which is static, and also we will cover the buoyancy force and stability. So buoyancy will be more on the application side, and we will see some of the information related to buoyancy. Okay, so for hydrostatic forces that we will be covering on the first part of our lecture today. So it will be covering more on the derivation of the calculations, okay, and the usage of calculation in order to determine uh, the values. Because when we are designing something underwater, so there will be a lot of factors affecting the performance of whatever system that we are doing. Okay, so you as an engineer, when you are coming to design a system or a robot or something that is moving underwater, so we need to always do a thorough calculation before determining so what type of material we want to use, what type of effect the body, so body means is the object, will undergo. So everything we need to take into consideration. So recently we know there was the implosion case, okay, of submarine. Okay, so the Titan submarine, so which went underwater to do some studies. So it imploded because lack of knowledge and lack of scientific calculations related to the pressure. Because we know as we go deeper in the water, the pressure will increase. So the material that we are using for our submarine or our ship so must be able to withstand the pressure, the high pressure underwater, especially if you plan to go into deep. Okay, so understanding about the hydrostatic forces is very important. Okay, so we will enter into introduction to fluid statics. So fluid static also known as hydrostatic. So hydro means water or fluid, and static means it's not moving. Okay, so we call it as hydrostatic. Okay, so fluid static deals with problem associated with fluid at rest. As I said, the fluid is not moving. So it can be a dam, so it can be a pond, so where the water normally will be stagnant. Okay, so there will be a different calculation from the dynamic fluid, like in river. Okay, so in fluid static, there is no relative motion between adjacent fluid layer, and thus there are no shear or tangential stresses in the fluid trying to deform it. Okay, so what it says, no movement between the layers. Okay, fluid normally will have layers. Okay, so since it's not moving from one point to another point, so no tangential stress. Tangential stress meaning stress at the surface level. Okay, so meaning if you have water on the surface, if the water moving from one point to another point, so it is moving because it's finding a equilibrium point. Okay, for it to stay. So that's why it's moving from one point to another point. So we call it as a shear stress or tangential stress. I think we have covered this in the previous chapters. Okay, so no adjacent and no relative movement. Okay, that's why the fluid is at static. The only stress we deal with in fluid static is the normal stress, which is the pressure, and the variation of pressure is due only to the weight of the fluid. So when we say weight, is related to gravity. So as we know, as it's closer to the earth core, so the pressure will be more compared to higher. in higher place or in higher altitude. Okay, so similarly underwater also the same, because underwater, so we have the surface, the surface, I mean the bottom of the sea. Let's say we are considering a sea, so the bottom of the sea which is connected to the earth, and also the water. Okay, so as it goes down, it will be closer to the core of the earth. So the gravitational pull will be stronger at the bottom of the lake or the pond. Okay, so the only force that we will be acting on, or the stress we are acting on, is the normal stress. So no tangential stress, but normal stress is the vertical stress. Okay, meaning going upward or downward. Okay, so that's the only stress that we will be dealing with. Okay, the design of the many engineering system requires the determination of the force acting on their surface using the fluid static. Okay, so as I say earlier, so when we are coming up with the engineering system, so when we are designing it, so we mechatronic engineers, we cannot be away from all this designing. Okay, so because we are dealing with mechanical as well as electronics. Okay, that's why mechatronics, so mechanical and electronics. So we will be dealing with development of the system, we will be dealing with designs. Okay, so when we design, so we need to determine the forces acting on the surface. Okay, surface meaning the surface of the body. Okay, so like water tank, ROV. Okay, so we have underwater uh, equipments that will be dealing, so for surveillance or checking. So for, even we have all these underwater welding. So a lot of apparatus are designed to perform operation underwater, especially in the deep oceans and deep sea. Okay, as well as we have like a mobile version of robots. Okay, like here we have a alien water-driven robot. So it will power by the water movement or water stress. So it will create the energy so that the robot can move around. So it can be a big system or small system. So everything need to be determined. Okay, so just as a revision, so we try to study back what is absolute pressure, atmospheric pressure, and gauge pressure. Okay, before we go to slide, so absolute pressure is the real pressure. Okay, real pressure. So atmospheric pressure will be something that depending on the places. Okay, so higher altitude will have different atmospheric pressure. Lower altitude maybe will have a different atmospheric pressure. It will change according to the places. And the gauge pressure is the pressure that we measure. Okay, gauge meaning is a device. Okay, so in Malay we call alat pengukur tekanan. Okay, so gauge pressure meaning the pressure. So that's why most of the device it will start from zero, but practically it is not zero around, because there will be some pressure acting on the body due to atmospheric pressure. But for us to easy to understand, so we start from zero because we are only measuring the gauge pressure. Okay, gauge, not GAG, yeah? GAUG. Okay, so what is pressure? So pressure is a normal force exerted on a fluid per unit area. Okay, so you take a area and we are applying a force. So that is what we call as a pressure. Okay, so pressure usually will be measured with bar or atmospheric pressure. So 1 bar equals to 10 to uh, power of 5 Pascal. Okay, so SI unit is Pascal. And one atmospheric pressure is 101,325 Pascal. So this is a standard one. But if you want to find a relative atmospheric pressure, so you need to measure according to that place. Okay, then we will know. Then what is absolute pressure? This is the actual pressure at the given position. Okay, so this. The actual absolute pressure consists of atmospheric pressure as well, and we have a gauge pressure. So the difference between the absolute pressure and the local atmospheric pressure. Okay, so we have a local atmospheric pressure. So pressure at that atmospheric pressure at that point. Okay, so we want to find the differential. Okay, so then we have a vacuum pressure, a pressure below atmospheric pressure. So we call it as a vacuum pressure, and we have an absolute pressure, absolute vacuum. The absolute vacuum is something that is not possible to happen on the Earth because we are dealing with gravity. But maybe in the outer space, there will be absolute vacuum where pressure equals to zero. Okay, so you can see from here, from a absolute vacuum to the local atmospheric pressure, we call it as a atmospheric pressure, and from atmospheric pressure upward, so the one that we measure, we call it as a gauge pressure. Absolute pressure is from absolute vacuum until the current pressure. So that's why when you are designing a system, don't depend on gauge pressure. Okay, don't depend on gauge pressure because gauge pressure is not so accurate. Uh, you need to consider absolute pressure because this will be starting from the real zero until the current pressure. So it will be more accurate. Okay, so just to do a revision, so variation of pressure with depth. Okay, so underwater, so Z is the depth. Okay, the height underwater. So as the so let's say here on top here is the surface of the water. So as it goes deeper, so you can see the arrow it keep on increasing. So the pressure will increase because we will have a surface here. I mean the bottom of the sea, which is connected to the earth. So we have a earth core below. So when it's closer to the earth core, the pressure will be more. So by that understanding, so we know that as it goes deeper, so the pressure will increase. Okay, and the pressure at the same point. Okay, so here the height is Z2. So if the height is the same level, and the density of the fluid, so let's say it's water, is the same, then the pressure will be the same. Unless a part of it is mercury, uh, then the pressure, even though is at the same point, so it won't be the same. Okay, similar here. So on top, the pressure is lower than the bottom. The bottom we can see the height Z1. So the pressure P1 is all uniform. Okay, so here it will increase because of the depth. Okay, so some derivations. So once we derive, then we can see some derivation here from. So it all from F equals to ma. Okay, so Newton's law. Okay, so we know that when the variation of density with elevation is known, so let's say the density is not same as it goes down. So maybe because of some special condition, or because maybe there's a oil leakage on the sea. Then maybe the density won't be the same, so we can find the differential. Okay, so how we can calculate? Okay, so this is the surface. So let's say you have a container you fill with water. Okay, so there will be a surface. So usually the surface is the top part of the water. Okay, the top part, it will be connected to the atmospheric pressure, the local atmospheric pressure. So let's say you have a cup of water. So you put, so the top surface will be connected to the atmospheric pressure. So the top pressure or the P above, the pressure above, equals to atmospheric pressure. So in the calculation, normally this atmospheric pressure will be given. Okay, so we know the top part is uh, atmospheric pressure, and as it goes deep, so let's say you want to measure a point here, okay, at this level, so we know the height is h. Okay, so P below equals to, so whatever here the surface pressure, or P above plus rho gh. Okay, rho gh. Okay, so P equals to P ATM plus rho gh. So this is how we can calculate. Okay, rho gh, so density. Yes. So anyone have any question? No. Okay. Please hold on. Okay. Okay. So density. So let's say if density, the fluid is water, so then you take the density of water. If oil, you take the density of oil. Okay. Gravity is the same, 9.81, and h is the depth. Okay. So normally will be given. So then you can calculate the pressure at the below point. So so let's say you want to just measure the pressure at this point without considering the atmospheric pressure, then you can take the gauge pressure. Gauge pressure, you don't need to, the atmospheric pressure, we start from zero. So we only measure the rho gh. So we can know the gauge pressure. Okay, so in a room, we know, I think we have seen this example before. So pressure at top, so let's say is one atm. The bottom will be slightly increased because of gravity, because it's closer to the earth core. Okay, underwater also the same. Okay, underwater on top will be lesser than the bottom. So that's why here. So let's say here the atmospheric pressure is 101 kilopascal. So down will be maybe 102 kilopascal. So slightly higher. Okay, so I think you have seen this in your midterm exam. Okay, so we can see, so there's a water. Okay, we have a surface. So surface is atmospheric pressure. As it goes down, pressure increases, and the height is h. So we have a point. So maybe the bottom part is uneven. Okay, normally we cannot find a ocean with a even surface. So normally it will be high or low, but it doesn't matter as long the height is the same. The height of A, B, C, D, E, F, G, all are the same from the surface. As long is the same and it is under the same density, so same fluid. Okay, here fluid, here we have mercury. Okay, but A, B, C, D, E, F, G, all under the same fluid, which is the water. So all are the same. The pressure will be the same. So PA equals to PB equals to PC equals to PD equals to PE equals to PF equals to PG equals to, so atmospheric pressure PATM plus rho G H. So it will be the same. But if you see H and I cannot be the same with above. It should be higher. Why higher? Because it's even deeper. So H plus maybe some H plus A. So let's say, so the distance from the surface is higher. But the second condition is not meeting because here you have mercury and here water. So the pressure won't be the same. pH not equals to Pi. Okay. So pressure in the fluid at rest is independent to the shape or cross section of the container. So that's why you see it's uneven. So it changes with vertical distance. So vertical distance is this. Okay, so the important part is the distance from the surface, but remain constant in other direction. So remain constant with the same direction, it will be remain constant. So just we need to check whether it's in the same material, because if same different material, the density here will be different. Okay, mercury is 13 times of water, so automatically this pressure will increase. It won't be the same as water, so it won't be the same, even though it's sharing the same depth. Okay, then Pascal's law so came in your exam also. So all these are just a revision. We have studied this earlier, but it's okay. It's good to do some revision. Okay, Pascal's law. The pressure applied in a confined fluid increases the pressure throughout by the same amount. So that's why we always have this doubt. How in car workshop you just press, you just apply a small force, but you can lift the car. So it's because of the Pascal's law. Okay, what Pascal's law say? So we can see there are two pistons. So piston A and piston B. So piston one and two. So when you have a piston, so you have its own area. So here it will be normally smaller than this. Okay, area two. But when you but this system is connected to the same fluid. Okay, it's not like this is one piston, this is one another piston. It is connected by liquid, the same liquid. Okay, so let's say it's a hydraulic oil. Okay, so when you apply a force here, so let's say you press the lever, so you keep on pressing, so this will increase, and it will lift the car. So the force one equals to P1 A1 equals to P F2 force 2 equals to P2 A2. Okay, so pressure at 1 and pressure at 2 will be the same, and you rearrange. So F1 over A1 equals to F2 over A2. So you rearrange again, F2 over F1 equals to A2 over A1. Okay, so the area ratio A2 over A1 is called the ideal mechanical advantage of the hydraulic lift. Okay, so this point. So when you apply a small force, so that's why it can increase the or elevate the car to a higher place, because the distribution of force will be the same, even though the force is greater. Yeah, so this is one application that really useful for our daily life. Okay, because so many things are depending on this. Okay, even in the big industry like forklift. Okay, forklift. So we have car jack. So we have even in the ports. So a lot of application that are related to Pascal's law. Okay, so you like in exam that day. So I asked her to explain the Pascal's law as well as give a real life example. So they can give all these example. Okay, so how we can measure the pressure? So pressure measurement devices. So we always will measure the atmospheric pressure using a barometer. Okay, so we can see this barometer in a meteorology department, where they will be measuring the atmospheric pressure changes. Okay, or it can be available in your science lab. So you can see some setup like this. Okay, so you have a container, and you have a uh, inverted tube. Okay, inverted tube. Okay, so atmospheric pressure is measured by a device called barometer. Thus, the atmospheric pressure is often referred to as the barometric pressure. So, barometric pressure is another name for atmospheric pressure, because we are using the barometer to measure the atmospheric pressure. Okay, so we will see. So that's a area here and point B to point C. Okay, so the same concept. Okay, so you can see there's a vacuum here. So here is supposed to be a atmospheric pressure because this point B, is at the same level with the atmosphere. Okay, so you're supposed to have an atmospheric pressure, and let's say you have a point here. So we weight a small molecule or small particles or small weight. So it's supposed to be rho g h a. So a is the cross section area, and it will be opposing the atmospheric pressure. So based on that, so we can measure here how much it can oppose. A frequently used pressure unit is the standard atmosphere, which is defined as the pressure produced by a column of mercury 760 millimeter in height of 0 degrees under standard gravitational acceleration. So that's why we are using a mercury inside. Okay, so mercury, so it will be more heavier, and we want to see how it can increase 760 millimeter in height at 0 degrees Celsius. Uh, so based on that, we can see how much atmospheric pressure is trying to push the weight. Okay, so let's say you have a multiple barometer, so different size. Okay, so the length or the cross sectional area of the tube has no effect on the height of the tube column of a barometer, provided that the tube diameter is large enough to avoid surface tension. So capillary effect we have seen last week. So as long it don't have a capillary effect, so uh, like the meniscus, so we try to neglect that. But if we see, so this is like having a larger cross sectional area compared to this and this, but the one that we concern is just the height. So the height will be the same. So I don't know whether you have done this in your house or not. So you try to take a cup, you try to put inside the water. So you take two cup and put inside the water. So when it's at the same level, uh, if you hold the cups at the same level inside the water, inverted, so the water will be the same, even though it's not connected, because when it's at the same level, the atmospheric pressure that is acting to push it up will be the same. So that's why we can see the water will be the same throughout uh, the level, even though it's not connected. Okay, so then we have another device we call as a manometer. Okay, so manometer, it is commonly used to measure small or moderate pressure differences. So we want to measure a small or medium, because normally the manometer will not be too long. So normally it's just like a carrying size. So we can measure a small or moderate pressure. So it is not suitable to measure high pressure, because it only can go up to here. If high pressure, so maybe if it's even longer, then maybe you can measure higher pressure, but it will be costly, and it's not worth it. So we just use a small setup to measure small or moderate pressure differences. So manometer, like barometer earlier, we want to find atmospheric pressure. Manometer, it is used to find pressure differences, because we have 2 points, point one and point two. We want to find the differences of pressure. Okay, so let's say in this case, so we have a gas, and we have a manometer here. Manometer normally it will look like a U, YouTube. It's not that YouTube. So it just the design look like U. So we call it as YouTube. Okay, so pressure P2. So P2 we know. So this is actually atmospheric pressure. So we have atmospheric pressure here because it is exposed to the atmosphere. So we have atmospheric pressure plus rho gh. Okay, rho gh. So we will come to this point. So this is P2. Okay, so you can find the differences between this and this. So normally the gas pressure can be known. Okay, so then we can also have different fluid at a container. So let's say on top is fluid 1, down is fluid 2. So let's say this is water, this is oil, this is water, and this is mercury. So you have three different fluids arranged. So it automatically will become like layers. Okay, layer 1, layer 2, layer 3. But one layer, so fluid 1 will be exposed to atmospheric pressure. So the top part will be H, uh, atmospheric pressure. Then the depth is H1, year to year. Then year to year is H2, and year to year is H3. So based on this, try to come up with this formula. Okay, so we want to measure pressure at 1.1. So pressure at point 1 is atmospheric pressure plus rho 1. So you cannot take rho anymore because different material, different fluid density. So density 1 times with gravity will be the same, and H1 plus rho 2 G H2 plus rho 3 G H3. Then you can get this formula. Then you can replace to find the value of P1. Okay. Then we also can have a special setup to find a pressure drop. The pressure drop, so you just incline this. This tube. Then you have a manometer. Okay. Then you have a tube. Okay, a bigger tube with a fluid flow. So you want to find pressure differences between pressure at point 1 and point 2. Okay. So for us to start the calculation, we need to find a common point. The common point is A and B. Okay, so same level. So you put it as the same level, then you can find. So PA equals to PB. Okay, because here is starting with the density rho 2, and B also at the same density. So the pressure will be the same height, same fluid density. So P pressure PA equals to PB. So how we can find the differences? So we try to find PA first, then we try to find PB. So what is PA? PA is pressure at 1. Okay, pressure at 1 plus rho 1. So this is rho 1. This is a water. I assume it's a water. Rho 1 G. So what's the distance from year to year? So A plus H, or H plus A. So we can find. So P1 pressure at PA equals to P1 plus rho 1 G gravity plus uh, times with H plus A. So we will get PA equals to, so now we find PB. So try to find the pressure at 2. So you have two different fluid density. So P2 pressure at 2 plus rho 1. So because it's the same width at this. So row 1 G A. Okay, so first one plus row 2, because this is row 2 density. So row 2 plus uh, row 2 G H, year to year. So you already know the two equation. So you already know some of the values. Now you rearrange. So if you, because you want to find a differential between pressure 1 and pressure 2. So P1 minus P2, you just rearrange. So you rearrange, so you can get this. After you solve it, at the end you will get P1 minus P2 equals to rho 2 minus rho 1 GH. This is after you settle. So the differences between this uh, point 1 and point 2 is actually the differences between pressure density 2 minus density 1 GH. So I is not doing having any effect, and gravity also don't have any effect, but the density is having a effect. Okay, or the pressure. Other pressure measurement devices. So we have a Borden tube. The Borden tube is something that we can see daily in our house. So maybe on a water filter. So normally we can see this kind of meter. The one this meter we call it as a Borden tube. So inside the Borden tube, we can find a hollow metal tube bent like a hook. This is actually hollow. Okay, when the pressure enter, so the pressure it will enter into the hollow tube inside. So when it enters, so it will try to straighten. Because of the pressure to straight this bent tube will try to straighten, and we straighten, so this will be connected to gear, and we can see the meter moves. Okay, the dial move from here to here, so it will measure the pressure. Okay, then we have a pressure transducers. So this more modern. Okay, last time it's more on the mechanical way. So now we have a pressure transducers because we have electronics. So we have microcontrollers, and we have all the other computer stuffs that can help. And we have these pressure transducers. Normally will look like this or something like smaller. It will use the various technique inside to convert the pressure into electrical effect, such as changes in voltage, resistance, or capacitance. Okay? So it will change. So when the voltage changing, or the resistance changing, or the capacitance changing, then you can relate it with the pressure. So pressure transducers are smaller and faster. Okay, compared to this, if modern tube, you need to wait until the gas goes in, then it will start to measure. But pressure transducers, they are much faster because normally it will be non-invasive, meaning no physical touch. So it will just measure by projecting some laser point or ultrasonics or some kind like ray. It will get the value, and it will be much faster. It will be more sensitive. Even smaller changes it can detect. It's reliable and used for a longer time and precise. Why is a longer time? Because it's not having any physical interaction with the fluid. Okay, like mechanical. You need to wait until the gas enter. We know when the gas enter or the fluid enter, so there will be a frictions inside. Because of the friction, After some time, you need to do a maintenance. So a lot of things. But since pressure transducers is more non-invasive, meaning is no touch, no physical touch, so less friction, less wear and tear. So it will be more reliable, and they are precise, more precise. So sometimes, if here maybe the smaller point is you can measure point 0.1, but here it maybe can go for a few decimal, 3 decimal or 2 decimal or 4 decimal. So it's more accurate. Okay, like for example, we can see at the petrol station. So if you go and fill the petrol, so we normally will see the digital meters. The digital meter, when you press the nozzle, so you can see the meter already start moving. So because they have a pressure transducers inside, so it's more reliable. So you can see even the liters, it can go up to 3 decimal. Okay, so let's say 20.564 liters. Uh, so it will be more accurate, but it cannot really be achieved with modern key. Okay, so then we also have a strain gauge pressure transducers. Strain gauge normally based on deformation of something, so it will detect the deformation. Okay, based on the deformation, it will relate it with the pressure. Okay, working by having a diaphragm defect, they are deflect between two chambers open to the pressure input. So it can be just a opening or closing of something. So when it open, it will check how much strain is measured, or it can be because of deformation. Then we have piezoelectric transducers. So piezoelectric is more electronics. So also called solid state pressure transducers work on the principle that an electric potential is generated in a crystalline substance when it is subjected to mechanical pressure. So piezoelectric is more on the crystal. So normally the sensor or the board, microcontroller board, we will have this crystalline substance. So we will see how much the crystal can generate uh, small electricity potential. So based on that, we can relate it with the mechanical pressure. So how much pressure? So this is more on the electronic side. So this will be more on the mechatronic side, and modern tube is more on the mechanical side. Okay, so any questions? So we finish with part one. So then we will continue with part two. Maybe I will just give like 10 minutes break. Please don't leave. I will take the attendance for part one.